Okay, so welcome back to the mid-year exam 2020 criterion 6 solutions. So this is question 2. A roller coaster trolley of mass 500 kilograms is at rest on top of a raised section of track. It then rolls down the track to a horizontal section 20 meters below as shown. The speed of the trolley when it reaches the horizontal section is measured to be 17.0 meters per second. Calculate the gravitational potential energy of the trolley at the top of the track relative to the horizontal section. Okay, so EP equals mgh, which is equal to, what was the trolley? 500 kilograms times by 9.81 times by 20. So what's that equal to? 500 times by 9.81. There's my funny nines again. 9.81 times by 20 is 98100 joules. You could say 98.1 kilojoules if you like, but you don't need to. Joules are fine. Calculate the kinetic energy of the trolley on the horizontal section of the track. Okay, so EK. Remember these formulas are on your formula sheet. It's equal to half mass times velocity squared, which is equal to half times 500 times by 17.0 squared. That is going to be equal to 250, times 17 all squared. So 72, 250. Oh, it's smaller than our potential energy. 72, 250 joules. Calculate how much energy was lost to the environment as heat as the trolley moved down the track. Okay, so we'll say heat be equal to EP minus EK. So the what's going on here is we have potential energy, and if there's no friction, if there's no energy lost, all of this potential energy would be transferred into kinetic energy down the bottom here. But because it's not, because it's less, there's some energy lost to heat. So it's transferred into heat and probably sound. So this is going to be equal to, what was it, 98100 minus 72250. Quite a fair bit of energy here being lost. So 98100 minus 72250 is equal to 25,850 joules. Excellent. Okay, question 2 is continued on the next page. A hoist is used to lift a 750 kilogram car 2.2 meters off the ground for a mechanic to work underneath. The hoist takes 15 seconds to lift the car through the 2.2 meters. Okay. Determine the amount of work done by the hoist on the car to achieve this lift. Right, so work is equal to change in energy, which is equal to mgh. So all we're doing is changing the height. So it's all just a change of potential energy. The mass of the car is 750 kilograms. 750 kilograms times by 9.81 times by 2.2 meters, which is the height. So we go 750 times by 9.81 times by 2.2. And it's equal to, let's put them all in. I might just go 3 significant figures. So 16200 joules. Okay, technically you could probably really only go 2 significant figures, but we'll go to 3. What is the power being produced by the motor driving the hoist? So remember, formula here, we've got P, average power here, is equal to work over time, or the change in energy over time. So P equals W over T, which is equal to 16200 divided by, so if you put in all the decimal places, you get a more accurate answer. I'm being a bit lazy. 15 seconds, time is in seconds. So there we go. 16200 divided by 15 is equal to 1080 watts. Okay, good. about a kilowatt. A racing car has a mass of 1,250 kilograms and is travelling at a speed of 150 kilometers per hour. When the driver pushes hard on the brake pedal, a constant braking force of 10,000 newtons is exerted on the car. Okay, determine the work in stopping the car. Right. Okay, so first of all, let's just say V is equal to 150 kilometers per hour divided by 3.6 meters per second. So that's equal to 150. So we're just converting to meters per second because that's what it has to be in. We're going to use our formulas. So that's 41.7 meters per second. So work equals change in energy. In this case, it's the change in EK. So it's equal to half times by 1,250 times by V squared, which is 41.7 squared. Just had to pause there because I thought, oh, they've given us our force. So, but they haven't given us a distance. If they gave us a distance, we could have done work equals Fs, but they haven't. So this is this way. We'll probably have to use it in the next one. It's continued over the next page. I'm probably jumping the gun here, aren't I? Okay, let's have a, so let's just calculate this first. So 0.5 times 1250 times by 41.7 squared. It's a lot of work. What's that? Almost a megajoule. 1, 2, 3, 4, 5, 6. Just a lot. Okay. I'm going to go to three significant figures here. So we're going to say 1.09 times 10 to the 6 joules. Okay. It's equal to 1.09 megajoules. So that's a lot. How far does the car travel after the driver has applied the brakes? So this is where we have work equals Fs, like I was kind of talking about before. This is where we use our force. S equals W on F. 1.09 times 10 to the 6. That was right, wasn't it? Let's have a look. I just want to make sure. Add 1, 2, 3, 4, 5, 6. Perfect. 10 to 6. How many zeros here? That's 10 to the 5. Divided by 10 to the 5. Okay, so that's going to be equal to 10.9 meters. So basically, because you can just cancel these out, so it's 10 to the 5, that cancels that down to 1. So it's 1.09 times 10, so it's 10.9 meters. Cool. 10.9 meters. This time the road is slippery. Predicted this would affect the work done in stopping the car. And explain why. Okay, did we assume? Well, it would. Okay. Right. This time the road is slippery. Predicted this would affect the work done in stopping the car. And explain why. So, yes, it would affect it. Affect the work done. The work done in stopping the car. It would. Would it? Now I'm trying to think. No, it wouldn't actually. No, it wouldn't. Look at me jumping the gun. It would not affect the work. I'll explain why. Since W equals change in energy, and it still has the same initial energy. And then energy of 1.09 megajoules. The distance would change. So it would take, the distance would be longer. As frictional forces would decrease. Okay, hopefully that makes sense to you. Basically, when the road is slippery, there'll be less frictional forces, so it would take longer to stop the car, but the amount of work done or energy required to stop the car would still be the same. Oof, these are long questions. Hopefully, okay, 2 more parts. In Tasmania, large hydroelectric dams store water used to generate electricity by falling and flowing through large turbines. In one particular power station, 1.00 times 10 to the 6 kilograms of water flows through turbines each minute after falling at a vertical distance of 50 meters. What theoretical power should be available due to the mass of water falling 50 meters vertically? Okay. What theoretical power? Okay. P equals change in energy over time, which is equal to mgh, so 1.00 times 10 to the 6 times gravity times 50.0. So I'm using EP. Remember, EP equals mgh over time, which is 30 minutes, so 30 times 60 seconds. Wow, quite a lot in that one. Let's put that into a calculator. Put brackets around the top one. So if you're not sure, you need to put brackets there. So we have 10 to the 6 times 1, so 10 to the 6 times 9.81 times by 50, divided by 30 times 60, which is equal to 272,500. That's in watts, or 272.5 kilowatts. Okay. When measured, the turbines in this power station develop a maximum power of only 5 point. So what have I done wrong? I reckon the power is just equal to n. That's right. We don't need. What does it say? Oh, each minute. Oopsie daisy. Each minute. So it's just equal to 60 seconds, right? Divided by 60, not 30. Divided by 60. That's what I've done wrong. Making a few mistakes. I must be getting tired, I reckon. Let's erase all this. Okay. Divide by 60. So let's do that again. Okay, that's better. So 8.175, that's a bit better. So 8.175 times 10 to the 6 watts, or 8.175 megawatts. Okay, that's a bit better. When measured, the turbines in this power station develop a maximum power of only 5.0 times 10 to the 6 watts. Why is this significant difference between the theoretical and measured power of the power station? Because of energy losses due to friction. Okay, good. And we'll leave question 3 for another video.